Okay, so this is lesson 5.6, the multiplication rule for independent events. So I think this is what we learned the other day. So multiply, you know, this is the general multiplication rule that you could use. We read this, the probability B, given that A has happened, if it's equal to the probability B, because in other words, if event A doesn't have an effect on B, then those two things would be equal. Well, that's what independent events are, right? So independent events means the first event has no effect on the second event. So if I flip a coin and then roll a die, flipping the coin, the outcome of that does not affect the die roll, right? So those are independent events. So you multiply. This is something you might have done the ACT actually. So you just multiply the two events. How many, if you have 3 pairs of pants and 2 shirts, how many different outfits can you wear? 3 times 2, you can wear 6 different outfits. So those are independent events. So this is the rule I want you to write in your notes for independent events. This is our formula of the day. If you want two things to happen and they're independent, all you do is multiply the two probabilities together. It only works for independent events though. Okay, so let's look at some examples. See if this might start to make sense. I think it helps. Okay, so suppose that Pedro drives the same route to work on Monday through Friday. His route includes one traffic light. The probability that the light is green is 0.42, yellow is 0.03, and red is 0.55. It seems like that's the chance of red, yellow, or green at all times. There's no difference between the day. What's the probability the light is green on Monday and red on Tuesday? So the chance that it's green on Monday, 42%. Chance that it's red on Tuesday, 55%. What's the chance that both of those things happen? Are they independent events? So we think the day of the week doesn't matter. That those probabilities are always true for this light. So we don't think that makes a difference. So you're just going to multiply those two probabilities together because they're independent events. So knowing whether or not it was green on Monday or red on Monday does not affect the probability on the next day, right? It's going to be different. So by the multiplication rule, we can say probability of A times B. So in this case, 0.42 times 0.55 is 0.231. There's about a 23% chance the light will be green on Monday and red on Tuesday. So these kinds of questions are going to be asking, we want both of those things to happen. What's the probability that Pedro finds the light red on Monday through Friday? Red on Monday through Friday. So Monday, Tuesday, Wednesday, Thursday, Friday. That's 5 times happening. Okay, so this is something that's going to be 5 times. So you got 5 things you're going to multiply together. So we can extend this. So we want to get red lights every time. The probability of red light is 55% the first day, and that's 55% the second day, and 55% the third day. So you're going to multiply all those probabilities together. Because those are independent events, it's 0.55 times 0.55. If you want to do that 5 times, it's not 0.55 times 5, it's 0.55 to the 5th power, or 0.0503 is what that ends up being. There's about a 5% chance that Pedro will encounter red light on all 5 days. You're right. I mean, one of those days you're going to get lucky, right? So this is actually kind of a sad but true example here. So in January 28th, in 1986, I think I remember this happening actually, where I was at school. Exploded on takeoff, and it actually killed a teacher, I believe. A bunch of people, 7 people. But they determined that the failure was O-ring joints and the shuttle's booster rocket was to blame. So experts estimated that the probability that each individual O-ring was a chance of working was 97.7%. Well, that's pretty good, right? But there were 6 of those guys, and they're all independent of each other. And for the launch to be successful, all of those O-rings had to work successfully. So that's 97.7% chance of living. That's not too bad, right? But if you have 6 of them, what do we have to do with those? You're going to multiply all those probabilities together. So 0.977 to the 6th power. Well, that's only, 87% chance. So they didn't know those O-rings were going to fail at that rate. I don't think they would have launched because the launch had an 87% chance of working, of all the O-rings working and no explosion. So that's not great. I don't think I would have gone up in space if I knew there was only 87% chance of living. So you can see that even though that each individual probability, because it had to happen, all of them have to work. One of them might fail, and that's the chances there. So if all 6 fail, 0 are good, 5 fail, 1 is good, etc. So that's just saying that. But if at least one O-ring fails, so, oh, that's interesting. So now, how do we figure out that at least one O-ring fails? So that's a lot of different calculations to do, because I'd have to think about the order. I'd have to do all 5 situations there, six different situations actually. So it might be good to use the complement, right? The complement of at least one O-ring failing is that they all work, right? So, so we're going to figure out the probability of them all working. So we know, we just figure out the chance of them all working is 87%. So the chance of at least one of them failing would be 13%. So that's where the complement really comes in handy. It actually saved us a lot of work, though. The other way of figuring this out is, oh man, so much more work. You have to do like 6 different equations. Actually, think you'd have to do it multiple times. So the complement is a very nice way of thinking through things, for sure. On some of the tougher problems, that really helps. Many people who come to clinics tested for HIV don't come back to learn the test results. Well, that kind of defeats the purpose, right? So now they use something called rapid HIV tests. I'm guessing these are not quite as effective, maybe. I'm just guessing. In a clinic in Malawi, use of rapid tests increased the percent of clients who learn the test results. Wow, so a lot of them come back for that one because it's fast. But the trade-off is that rapid tests are often less accurate than slower laboratory tests. That makes sense to me. Applied to people who have no HIV antibodies, one rapid has a probability of 0.008 of producing a false positive. But that doesn't seem too bad, right? If a clinic tests 200 randomly selected people who are free, don't have HIV, what's the chance that at least one false positive will occur? So, so we want to get at least one. So that seems like the last kind of question. So I'm thinking, maybe what's the chance that there are no false positives, right? So what you could do is the chance of no false positives. So let me just show you in Scratchpad here. So you go, okay, so you've got 0.008. So the complement of that is 1 minus 0.008, which is 0.992. So there's a 0.992 chance of not having a false positive, right? So if there's 200 people, that's going to happen for all 200 people. So I think you take that to the power of 200, which is that. So that's the complement of that, the event happening. So if there's a 20% of the event of it not being right, so that means that it's 80%. Ooh, this is not good. If there's a lot of people, even though it looked like a really good percentage there, this is going to be, so the answer is actually the complement of the 0.201, right? So there's a 79.9% chance of getting a false positive. Ooh, at least one. Does at least one. So maybe not all of those are false positive, but at least one. So 1, 2, 3, 4, or more false positives. I don't like that as much now. So use the multiplication rule for independent events wisely. Yeah, so you just have to only use it for independent events is key. They have to be independent. So, and there's a difference. This is just kind of like a side note. There's a difference. We've talked about independence. The events don't affect each other. Mutually exclusive means they cannot happen at the same time. And those two things don't overlap. I think that's probably what this is saying. Do you see how the independent events, you can have some overlap there, but mutually exclusive, you really can't have any overlap because those are two separate things, right? Because in mutually exclusive, it means if event A has happened, event B cannot even happen. They can't happen at the same time. Government data shows that 8% of adults are full-time college students and that 30% of adults are 55 and older. If we randomly select an adult is full-time college student and over 55, So are those independent events, I think is what they're asking. So is there overlap between the seasons? So government data shows 8% of adults are full-time college students and 30% of adults are age 55 and older. I think they're not mutually exclusive, right? They can happen at the same time. So it could be overlaps. So are they independent? I guess that's the question. So no, because being a full-time college student and being 55 or older are not independent events. So why are they not? You might be able to show it with a formula, but also like if you're over 55, you're not that likely to be a college student. So I think they don't sound independent to me. Like I think if you're younger, you're more likely to be a college student if you're a younger adult. If you're an older adult, you're less likely to be a college student. They just don't. So knowing whether your age will, or if you're a college student, might help me predict your age. If you're a college student, I'm going to predict that you will be on the younger side of things, typically. Simplification gives another way to do it. So we could, two-way table summarizes the data. Are the events taco tongue and B, evil eyebrow, independent? So if knowing the one event happened doesn't affect the other event, so probably the taco tongue and evil eyebrow is 21%. So both those things can happen. But if you multiply the two events, multiply probability of taco tongue times evil eyebrow, you don't get the same value there, right? They're different. Since the probability of A and B and the probability of A times the probability of B, they are not independent events because those two things are not equal. It's another formula way we could prove if two events are independent or not. If the ability to roll one's tongue and the ability to raise one's eyebrows were independent, then about 23.1% of students would be able to taco tongue and evil eyebrow. Remember, that was the thing. If they're independent, it's 23.1%. But it's not independent because that's not the percentage. We got 21% that can do both. Only 21% can do both. It's not what we expected if they were independent events. Is there a connection? Well, it's impossible for them to happen at the same time. And there at the bottom, it says two mutually exclusive events. Remember, they can't happen at the same time, can never be independent because if A has happened, B cannot happen. So you can't have two events that are both mutually exclusive and independent. It's impossible. Okay, that's your lesson for today.